Dr. J.V. Tyagi, Director NIH, Dr. Gwyn Rees, Area Head, Water Resources, UK Center for Ecology and Hydrology, my colleagues from IIT Roorkee and NIH, and dear students. Today we are celebrating here World Water Day, which was initiated in 1993. Have the awareness among the people about the importance of the water, its use, and tackling the water-related issues. Because in case of water, issues may be in both the cases, whether it's availability in abundance or scarcity. Roorkee is the hub of water engineers. And today all the departments working in the area of water, including NIH, will be deliberating on the subject. And to celebrate this day, we have invited Dr. Gwyn Rees from UK Center of Ecology and Hydrology, who is well-known water expert and working with IIT Roorkee and NIH for quite long. So without taking much time, I now request Dr. Gwyn Rees to share his presentation and deliver his talk. Dr. Rees, I think you can hear me.
I can indeed.
Okay, very good evening. Share your presentation.
Good evening to you too, and I hope you can see my screen.
Yes.
Great, okay, I shall start then. So, namaskar, good afternoon everybody, and happy World Water Day to you all. It is a great honor to have been invited to give this talk to such an august body of water experts. I'd like to thank Professor Arun Kumar, Professor S.K. Singhal, and Dr. Tyagi for granting me the privilege. In keeping with the theme of World Water Day celebrations in Roorkee, I shall be setting out the role of sustainable catchment management has in safeguarding the value of water and the role we as scientists can play in that effort. So what is the issue? What is at stake? Population, urban and economic growth over recent decades has resulted in an unprecedented demand for water in all parts of the world. Yet pressures such as land use change, intensive farming, urbanization, and climate change are increasing. Freshwater ecosystems are being degraded at alarming rates, and in many places the quality of water is deteriorating to such an extent that it cannot be used and is becoming a threat to human and animal health. All over the world, there is huge concern over the future resilience of our water supplies and of our future water security. We all know how important, how vital water is to all aspects of life. But how do you place a value on water? I'd say we're all familiar with hydrological disaster being quantified in terms of economic damage or loss. The financial losses incurred as a result of a flood or a drought, for example. And to justify investment in infrastructure, we almost always need to express the benefit economically in terms of prevented damage or perhaps avoidable loss. It is somewhat more difficult, however, to place a value on the basic, raw and natural commodity of water. How do you place a value on something that is so essential to life? How do you place a value on the benefits it brings? And in a country like India, how do you place a value on its social, cultural and spiritual importance? Economists, I should say, have been trying to do this for many years. Indeed, valuing nature in recent years has given rise to a new term and a new discipline of natural capital accounting. Natural capital accounting is a recognition that the natural world contributes to our livelihoods and prosperity, that natural ecosystems provide essential goods and services that have an economic worth. It provides a framework to better account for nature in national economic planning and policy decision-making, and it is an approach that is gaining traction all over the world. And it is good to see, I think, India also adopting this approach, with the National Statistical Office now mandated to prepare India's own national resource accounts. But I am myself no economist. I'm a simple hydrologist. And so, if I may, I will return to more familiar ground and the topic of my talk, sustainable catchment management, and how it can safeguard the value of water. So what is sustainable catchment management? Traditional engineering approaches of building grey infrastructure, that of diverting rivers, building pipelines and erecting dams, is not the most environmentally friendly way of addressing the demand for water, and neither is it the only way. Increasingly, water managers and planners are turning to environmentally sensitive and sustainable nature-based solutions as a low-cost, effective means of helping to improve water security. Sustainable catchment management, or SCM for short, can be defined as the effective, integrated management of land, soil, water, and waste within catchments. SCM embodies the principles of sustainability, conservation, and restoration. It is aimed at protecting water sources, safeguarding water quality, and attaining good ecological status of freshwater bodies. Similar in concept to integrated water resources management, SCM requires a whole system approach from source to sea, involving stakeholders from many different disciplines. As scientists, there are many ways that we can contribute to sustainable catchment management and to safeguarding the value of water. I will be presenting some examples of this in my next few slides. It is estimated that some 80% of the volume of fresh water on which humanity depends is generated in the mountains and the uplands. It is vital, therefore, that science contributes to the sustainable management of water in such areas. Several studies have shown climate change, and rising temperatures specifically, is occurring fastest in mountain and upland areas. Understanding climate change and its likely impacts on downstream water availability is key to effective catchment management. Changes to snow and ice in high mountain areas is a particular interest to me personally, and indeed it was the subject of my PhD not so many years ago. As the most striking and visually obvious evidence of climate change, glacier shrinkage and reduction in snow cover continues to attract attention. A recent example of this is the UK-India Sushiwat project that involves staff from both IIT Roorkee and NIH, involving the likes of CSB Ojha and Sanjay Jain. Another key area where science can make a difference is in the understanding of natural hazards, floods, landslides, and glacier lake outburst floods. The latter certainly is a hot topic given the recent disaster in Uttarakhand. Also, there's much more to learn about the processes affecting soil erosion and sediment transport in the uplands, problems that seriously impact hydropower generation and reservoir operation, especially in the Himalayan region. And despite many years of research, there still is some uncertainty about the effects and benefits of afforestation or deforestation on floods and low flows. A relatively under-investigated area of research, in my opinion at least, is the role of high mountain peatlands, wetlands and lakes. Not only are they important sources of fresh water, but they also provide a range of additional and vitally important ecosystem services, such as carbon sequestration, flood mitigation, habitat provision, and for local communities, they often are a source of food and support the livelihoods of many people. Yet even in the uplands, remote as they might be, problems of overexploitation, land use change and deterioration of water quality persist. As scientists, we must bring our expertise and understanding to bear to help protect and restore these most precious of environments. Moving downstream, diffuse pollution is a major challenge to sustainable catchment management that seriously limits the utility and value of water. Diffuse pollution occurs when pollutants leach into the surface and groundwater. The pollution typically comprises nutrients, mostly nitrates and phosphates that come from animal waste and fertilizers, chemicals used in the treatment of crops, and human waste or sewage. Eutrophication, which is an excess of nutrients in fresh water, is a particular problem that leads to the formation of extensive mats of floating plants, such as water hyacinth, and algal blooms, including toxic cyanobacteria. Diffuse pollution has a huge economic cost to society. In the UK alone, water companies spend millions of pounds annually treating polluted water and tackling sources of diffuse pollution. Some of the nature-based solutions that are being used to tackle diffuse pollution are listed here on the left-hand side of my slide. UKCH is playing a leading role scientifically in the battle against diffuse pollution. Internationally, we are leading with UNEP on the Our Phosphorus Future initiative, which aims to combat the global problem of phosphorus pollution. We are also leading an initiative called the South Asian Nitrogen Hub, tackling the problems associated with nitrogen from agriculture and the burning of fossil fuels. Specifically in India, with IIT Roorkee's Himanshu Joshi, IIT Kanpur's Rajiv Sinha and others, we recently have undertaken one of the most comprehensive water quality monitoring of the Ganga and its major tributaries, identifying and analysing sources of pollution. In a separate study with NIH's Thomas, Manish Nima and PK Mishra, we have been developing an integrated water resources management tool for the Narmada Basin. Together, we are in the process of developing a water quality extension that will help us understand the source and fate of pollutants. In yet another study, we have been working with VC Goyal and Omkar Singh of NIH and Himanshu Joshi again on the pollution problems of village ponds, providing guidance and advice on how to mitigate the problems and testing solutions such as constructed wetlands. Moving yet further downstream, according to the United Nations, by 2050, there would be an extra 2 billion people on Earth, and by then some 70% of the global population is expected to be living in urban areas. As hydrologists and water scientists, our efforts increasingly are focused on understanding the effects of urbanization and in finding sustainable ways to support urban living. There are various sustainable measures that city planners and urban dwellers can take to alleviate pressure on water resources and the environment. Improvements in demand management, water harvesting and grey water recycling, sustainable urban drainage systems, and applying nature-based solutions in city planning and design. This latter measure has been the focus of our EU-funded Regreen and Sponge Cities initiatives, in which we have been modelling urban ecosystem services of cities in Europe and China, and assessing the benefits of urban green and blue space on reducing air pollution and flood risk, and for improving water quality. Urbanisation, of course, puts much more pressure on water quality as well, as urban runoff and wastewater needs to be collected and treated before it can be safely returned to the environment and or reused. At UKCH, we apply advanced analytical methods to test the effectiveness of treatments in wastewater treatment works. Our methods can detect emerging contaminants and micropollutants in the discharges from the sewage works. And we use eDNA and flow cytometry methods together with water quality models to assess impacts on downstream ecology. In Bangalore, we recently have been working with A3 and IISc to understand and mitigate pollution problems on the city's urban lakes, or tanks as they call them there. We have been looking at the effectiveness of decentralized water treatment, such as constructed wetlands, in combination with STPs for improving water quality. The future challenges that we all face of climate change, population and economic growth, and associated problems of food and water security are well articulated and are well embodied within the United Nations Sustainable Development Goals. These challenges, which arguably are the greatest humanity has ever faced, present opportunities for science to seek new solutions and to demonstrate its worth to society. Such global environmental challenges will require widespread international collaboration and partnerships at a global scale. That's why partnerships such as the one UKCH has with IIT Roorkee and NIH are so important for us to build and maintain, irrespective of what you do to us in the cricket. So there you have it. Those were just a few examples of how sustainable catchment management related science can help safeguard the value of water. If anybody is interested to find out more or would like to explore opportunities for further collaboration, please do contact me by email. Thank you. Dhanyavad.
Thank you, Dr. Rees, for shedding light on the theme of World Water Day 2021. We got to know why it is important to safeguard the value of water and how it can be done through sustainable catchment management. Thank you. Moving forward, I now invite Dr. J.V. Tyagi, Director NIH, for sharing his views on the occasion.
Thank you, Professor Singhal. And good evening to all. Professor Chaturvedi, Director IIT Roorkee, Professor Singhal, Professor Arun Kumar, faculty members from IIT Roorkee, and my colleagues from NIH. It is really heartening that we are celebrating this World Water Day 2021 jointly. As you know, the basic aim of celebrating World Water Day is to raise awareness of the global water crisis. And as we all know, the water has enormous and complex value for sustenance of life, for production of food grains, for energy generation, for industrial production, and also for conservation and protection of biodiversity and environment. But the demand of water from all these sectors is continuously on rise, which is putting extra pressure on the already stressed water resources of the country. And as you know, in recent years, concern has also grown of potentially large but uncertain effects of climate change on water resources. So avoiding the water conflicts among various water user sectors, achieving water security and food security is fundamentally a matter of comprehensive understanding of the multidimensional value of water, demand management, and also efficient utilization of available water resources. So keeping these things in view, the planning and utilization of water resources has to be based on efficient or the economic efficiency, social equity, then conservation of ecology, and also protection of fresh water. I have a small presentation also from NIH. I'll not take much time, and I'll request Dr. Sudhir Kumar to make the presentation, please. Dr. Sudhir Kumar.
Good afternoon, Chaturvedi, Dr. Tyagi, and my friends. I'm going to make a small presentation on NIH, which is to give you an overview what NIH is, because many of our audience may not be aware about the activities of NIH and what NIH is. So I will be let you know a little bit about NIH. So NIH was established in the year 1978 at Roorkee, and it is located within the campus of IIT Roorkee only. We are a ISO 2015 organization. So the objectives of NIH are to undertake, aid, promote, and coordinate systematic and scientific work in all aspects of hydrology, cooperate and collaborate with other national and international organizations in the field of hydrology, to establish and maintain a research and reference library in pursuance of the objectives of the society, and equip the same with books, reviews, magazines, and other relevant publications, and to do all such things as the society may consider necessary. So this is an autonomous body under Ministry of Jal Shakti and Department of Water Resources. So this is the structure of National Institute of Hydrology. We are a society with a governing body and technical advisory committee, standing committee, and we have working groups and regional coordination committees to assist in development of our technical program. We have 6 scientific divisions at Roorkee headquarters, and these are the environmental hydrology, groundwater hydrology, hydrological investigation, surface water hydrology, water resources systems, and research management and outreach division. Then we have some laboratories on water quality, soil and water laboratory. Then we have nuclear hydrology laboratory, hydrometeorological observatory, remote sensing and GIS lab. Apart from the headquarters, we have 6 regional centers distributed all over the country. We have, these are mostly the thematic regional centers, which have some special theme to work on. The first regional center is Hard Rock Regional Center at Belgavi in Karnataka. It works on hard rock hydrology. Then we have Western Himalayan Regional Center at Jammu. Central India Hydrology Regional Center, basically to work on arid and semi-arid regions of India. Then Deltaic Regional Center at Kakinada. It works on the east coast, that is on the Deltaic region. Then we have Center for Flood Management Studies at Patna, Center for Flood Management Studies at Guwahati. So these are our divisions, which are located at Roorkee, and these are our regional centers, which are located in different parts of the country. So these are the laboratories which are very well equipped. We have nuclear hydrology laboratory, one of the best laboratories, and identified by even IAEA recognizes us as a good laboratory in India. Then we have very good equipment, DI IRMS, CF IRMS, carbon 14 tritium rating. Then we have for alpha, beta, and gamma measurement instruments. Then we have water quality laboratories with ion chromatograph, POC, etc. We have remote sensing and GIS laboratory with all the latest ArcGIS and DAS software, etc. Then we have soil and water laboratory with CHNS analyzer, particle sizer, ICP, OES, etc. These are the facilities. We have our own library, which is very well equipped. We are receiving many journals, international journals in our library. We have a very good auditorium with sitting capacity of more than 300 people, guest house, and then we have society room and lecture hall. Our main R&D capabilities are flood and drought studies, water resources system analysis, surface water and groundwater availability, hydrological modeling, water quality assessment and modeling, groundwater modeling and management, regional hydrology, impact of climate change, integrated water resources management, application of emerging technologies like soft computing techniques in hydrology. Then we have snow and glacier investigation facilities. We have remote sensing and GIS application, hydrology of lakes, software development. I mean to say that we are working on all the facets of hydrology in our institute, right from climate change to urban hydrology, isotope hydrology, etc., etc. In the isotope hydrology laboratory is one of the special laboratory in our institute, and we are working on identification of recharge sources and recharge zones of deeper aquifers and springs, effectiveness of artificial recharge of groundwater, salinization of groundwater inland and coastal aquifers and seawater ingress, groundwater and surface water interaction, recharge to groundwater due to irrigation and canal, groundwater flow velocity and direction, weekend seepage from reservoirs and canals, rate of sedimentation in lakes and reservoirs, separation of snow and glacier melt, and then interconnection of water bodies, etc., etc. Recently, our activities are focused towards the National Hydrology Project. As you may be aware, this is a project which is run throughout the country. Then we have development and implementation of the decision support systems for various states, National Mission on Sustainable Himalayan Environment. We have Indo-German Center on Riverbed Filtration, Innovation Center for Eco-Prudent Wastewater Solutions. NIH also holds the Secretariat of Indian National Committee on International Hydrology Program of UNESCO and Indian National Committee on Climate Change. Under NHP, our activities are mainly towards the purpose-driven studies. The main role of R&D section is to coordinate the research activities and to review, monitor, and progress the PDS. In the R&D sessions, total 9 sessions have been held. 14 projects have been approved and review of PDS are under progress. NIH has been assigned with the important task of planning and organizing a training program. NIH is the nodal agency for all the training and capacity building under NHP. Then we have a Center of Excellence for Hydrological Modeling, and we have decision support system, PDS under our NHP program. If we under decision support system, we have developed a number of decision support system. I will not read all. We have in Andhra Pradesh, Madhya Pradesh, Chhattisgarh, Odisha, Kerala, Karnataka, Gujarat, and Tamil Nadu and Maharashtra. We have developed a number of decision support systems with the state governments on various aspects of water management. Then, under the National Mission for Sustaining Himalayan Ecosystem, we have been given the task force 2 by DST, which relates to water, ice, and snow, including glaciers. And the basin chosen for that is Upper Ganga Basin up to Rishikesh. And under that project, we are having number of studies on development of hydrological database, real-time snow cover information system, glacier lakes and bluff studies, assessment of downstream impact of the Gangotri glacier system, hydrological modeling in Bhagirathi, climate scenarios, then aquifer interaction with and groundwater potential, understanding of hydrological processes and using isotope techniques, environmental assessment of aquatic system, water sensors, and hotspot analysis in selected villages. So that's all the major activities of the institute, which I wanted to bring to the notice of the audience. Thank you very much.
Thank you, Dr. Sudhir and Dr. Jaichu. It's interesting to see the role of NIH in the sector of water and hydrology. Now it's time to have department-wise presentations, and we'll start with Department of Hydrology. I request Professor M.K. Jain to start with.
Thank you. I think the ball is already set rolling in terms of securing water for future. So I'll just try to emphasize here is that we all know that we are facing water shortage. And the major reason for India to have this water shortage is the uneven distribution of the water. And something around 600 million people are facing this water stress. And estimate of Niti Aayog also says that in many parts of India, critical groundwater resources is already depleted. But the silver lining here is that if we go for proper management of our water resources, then a secure future, water secure future is possible. And again, even for a growing and more prosperous population, right? So the challenge is like how we can treat this water as a local resource so that we can think of localized solutions. And it is important to see this slide from Central Water Commission about the variability of the water throughout the India. There is a lot of variability, as well as you can see the temporal variability. So the water is available only in 4 months. So integrated water resources management is the key. And if you see the projected water demand, again, I have taken from NWDA. So by 2050, the per capita demand is going to decline drastically. And the index, if you see, if it goes below 500, then there is a primary constraint for human well-being. Usually we see that, okay, around 1,000 is in optimal condition. That is what is required. But if you see the conventional approach, that is the top-down approach, supply-led or technical-based sectoral approaches, they are unsustainably high economic, social, and economic cost on the human society and the natural environment. So we have to go for, first of all, understand economic efficiency in the water use so that water is finite, we cannot create. So how efficiently we can use it? Social equity, that's what Professor Tyagi highlighted, that we have to go for that water is available for all, and environmental and ecological sustainability of the water so that future generations, they can have water available. Now, what is the way ahead? First of all, assess, conserve, preserve, and manage. So at Department of Hydrology, we are doing a lot of work in terms of assessment of the water by looking at what is available at present, by looking at what are the future projections, what future climate change is going to have in terms of availability of the water in different basins. In terms of conservation, can we devise some methodology so the natural solution or the localized solutions like catchment treatment planning, rainwater harvesting, storing water where it is fall. So as the ministry is also saying that catch the rain where it falls. So that is the way ahead. Then you have to also see how we can preserve the quality of the water. So different solutions in terms of treatment. Department of Hydrology is also working a lot of treatment methods, including wetland studies and including phytoremediation, membrane technology, and so forth. And once we are able to preserve this water quality, then we have to look for the management aspect. So we are also working in terms of management aspect. As NIH is doing, they are a bigger organization, but of course we are also working in almost all facets of water. And this is the way ahead. We have to take water as one water approach, so that for all different purposes and for all requirement, treat water as a single resource. Try to take what social and economic inclusiveness of the water is there, put value to the water, and try to maintain healthy waterways. So that's what the message I would like to convey on this World Water Day. Thank you. Hello.
Very good afternoon to all. As we all know that today we are here to celebrate World Water Day. This World Water Day is celebrated to raise awareness so that we can provide clean and safe drinking water to over 2.2 billion people. Out of 7.9 billion people in the world, 2.2 billion people are still not able to access the safe and clean water resources. This is also main goal of Sustainable Development Goal 6. In that SDG 6, they are projecting to have clean and safe water by 2030. From the ancient time, the water was a precious liquid. What was used for cleaning today, this water must be clean to ensure our survival. Without food, human can survive for a number of days, but water is such an essential element that without water we cannot live. The value of water is about much more than its price. Water has enormous and complex value for household, food, culture, health, education, economics, and the integrity of our natural environment. If we overlook any of these values, we risk mismanaging this finite, irreplaceable resource. Today, water is under extreme threat from a growing population, increasing demand of agriculture and industry, and the worsening impacts of climate change. In this regard, as we all know that in India, more than 80% water is used for agriculture purpose. If you see the total water source of the country is around 4,000 BCM, but only we are able to utilize 1,123 BCM. If we see the per capita water availability, how it is changing with time, in 1951 it was around 5,000 cubic meter per year, but it is expected that by 2050 it will be around 1,140 when our population will be 1.6 billion. The main worry is if we see the per capita water availability in different basins, especially if we see the Brahmaputra and Narmada, they are in the range of say 1,500 to more than 1,500 cubic meter per year per day. But if we see the world average is around 5,000 cubic meter per year. How water is demand is increasing, and we all know that by 2050, when our population will be around 1.6 billion, at that time the food grain requirement will be around 475 metric ton. And at that time, the water requirement for agriculture will be around 807 billion cubic meter, and our total water resource availability will be around 1180 billion cubic meter. Since the demand for other sectors are increasing, definitely it will be really difficult to meet the demand of irrigation sector, especially if we see the irrigation sector is very helpful for the crop production, because the productivity of irrigated agriculture is 3 times higher than the rain-fed agriculture. So we cannot reduce the water use in agriculture sector. Even Niti Aayog has reported that 50% of the springs are Himalayan regions are drying, and this is also creating a threat to the around 20 crore people in the Himalayan states. So in Indian situation is groundwater is depleted, surface water is polluted, rainfall is wasted. population is increasing, demand is increasing, consumption is also increasing. There will be scarcity of water due to industrial growth, economical industry, water business, and since agriculture sector is the most contributor of the water resource, so we have to reduce the water use in agriculture sector for future sustainability. How we can do that? If we see the paddy production by China, they are using 500 liters of water. In India, we are using 2,800 liters of water. And overall, our productivity is only 3.6 tons per hectare per year, which is far below the world average, that is 4.5 tons per hectare. So we have to introduce some technology so that we can minimize the use of water in agriculture sector. In this regard, we are providing agro-advice services to farmer on every Tuesday and Friday, so that farmer are knowing in advance that whether there will be rainfall or not. With that, if farmers are adopting these agro-advice services, there is a lot of saving of water, not only water, even they are saving 500 rupees per hectare. In this regard, we have also developed one mobile app so that we are able to provide real-time information to the farmers. We are also doing one project with the National Water Mission to how we can improve the efficiency of water use, and definitely it is going to help a lot. If we can reduce the water use in agriculture, definitely that can be used for the other purposes. Thank you.
Let us speak on some issues that are related to the sedimentation in the Ganga River. We know that the sediment is an integral part of the water, okay? Once you see the carrying capacity of the water in terms of the sediment, okay, that is not balanced. In that case, that comes out in the form of the sedimentation or the erosion. In this slide, we can see that you see the major river basins of the India, and out of that, this Ganga River, which is having the most sediment load, right? Of course, the Brahmaputra is having higher than this, but the catchment area of the Ganga basin is much higher, right? And here this load is coming out to be 413 million ton per year, right? And if we see in the terms of the erosion rate, that is coming out to be 438 ton per square kilometer, that is the catchment area per year. And if you compare this figure with this average erosion rate worldwide, this is coming out to be 150 ton per square kilometer. That is very low. So this Ganga River basin, this is highly sedimented river, and there are various issues that are related with that. So we can see this is the basin of the Ganga. You might have seen that one, that is not new. Here we have done the sedimentation analysis in the Ganga River basin, right? Right from the Deoprayag to Farakka Barrage, which is in the terms of the length is about 1824 kilometers. These are the observational station of the CWC. CWC uses to measure the sediment concentration, and we have taken those data from this CWC of this period, and we have analyzed that. Now, see here the sediment load at the various stations, starting with the Garmukteshwar, and we can see here at the Gandhi Ghat. Gandhi Ghat is a CWC station, okay, at Patna, and Hapida is about 100 kilometers downstream of the Patna, near this Mokam. And that is having the most sediment load. You can see here at the Patna, this is about 216.3 million ton, okay, per year. And this is due to the confluence of the two major rivers, that is the Gandak River and the Ghagra, that are joining from the left bank, okay, in the upstream of the Patna. So here is the major sediment concentration. And if you go in the downstream, I mean further in the downstream like the Azamabad and finally at the Farakka, the sediment load is less. So this is indicating that there is a siltation in the downstream of the Azimabad. Now, if you see the barrages on the Ganga River, basically there are 6 barrages on the Ganga River. And if you see this one in the perspective of the sedimentation, the 2 barrages is, you see, suffering with the major sedimentation. One is the Narora barrage near the Narora, and second one is the Farakka, of course, that is the last barrage on this Ganga River, is about 15 kilometers of the stream of the Bangladesh boundary. And here, both the barrages is having a very major sedimentation problem. In the upstream, there is a lot of the sedimentation. In this Farakka barrage, you can see the sedimentation, how that is progressing. Okay, 1970 is about 256 or 258 a square kilometer area. That was, this is in the terms of the area. This much was the sedimentation, and in 2010 that increased to 385. So there is, due to that Farakka barrage, there is a lot of the sedimentation which is going on the upstream. The Bihar government is saying that, you see, all this sedimentation is causing the flood in the Bihar, but this is not well established. Such sedimentation load is bringing a lot of the morphological change in the Ganga River. I would like to show 1 or 2 slides here. See here, this is Diara, Raghopur Diara. Of course, in a technical term, we can say the island. And this Diara is not in the terms of just 1 kilometer or 2 kilometer. This Diara is 240 square kilometer. Although the area of this Diara that is go on decreasing due to the erosion process, but lot of the sediment load in the river system that is bringing such type of the major morphological changes here in the case of the sedimentation. Based on the study that we carried out on this river Ganga, you see we have proposed the protection works by analyzing the critical section. Critical section means, I mean, those reaches where there are major morphological change in the Ganga River. And you can see here in the Bhagalpur, the river has shifted away from the Bhagalpur, is about 12 kilometer from Roorkee to Mangalore, we can say. So this much is the shift in this Ganga River at the Bhagalpur. And due to that, what happens that if you have the water intake on this location, of course, that will be deprived of the water. Likewise, the other locations also, we can see this is the location, maybe some Munger. So this is near the Raj Mahal, further downstream, and here the protection works on the basis of the morphological study we have suggested and pass on to the CWC. Through the analysis, you see what we have concluded that the sediment load is not proportional to the discharge. We can't say that if the discharge will be very high, in that case, the sediment load that will be high. Okay, here we have seen that the moderate discharge is carrying the more sediment load than the high discharge. Because the sustainable, you see, the peak discharge that is sustaining only for a very short period of the time. So moderate discharge that is prevailing for a long period of the time, so that is carrying a lot of the sediment load. And in general, that's, you see, that is so-called effective discharge, and that effective discharge is about discharge of about 1.5 years return period discharge. So that are being calculated here. On that basis, of course, we have concluded, if we'll see on the basis of the sedimentation, the Ganga River that may be divided into 3 reaches. Deoprayag to Allahabad is about 26 million ton per year is the sediment load. Allahabad to Buxar, that is 108 million ton per year. Buxar to Farakka, of course, this is the lower Ganga basin, and that is having the major sediment load here. And if we'll see in the terms of this sedimentation, Buxar to Farakka, the sedimentation is 178 million ton per year. So this much you see is the sediment, the load, that is the, the siltate in the reach from the Buxar to Farakka, okay, 178 billion ton per year. For the further study, of course, we have submitted a proposal to the CWC, what further study that can be carried out in the terms of the sediment issues in the Ganga River, so that issues can be addressed. Thank you.
Good afternoon. So many things are already discussed by my previous speakers. So very few things are left, but I will try my best to explain some of the knowledge gap in Indian hydrological cycle. So basically, we have 16 to 18% of world population, and the land area is almost 4%, nearly 4%, and available water resources is also very less. So in this condition, we need to understand and manage our water resources very wisely. So the exponential increase in population, not only the population, the aspirations to live our life is also increasing. So in this way, the demand of water is much more as expected in different models. So we need our water resource to manage from beginning to stress and the available water supply in many parts of the country. So this is the annual water budget, the available water, and the potential flow in rivers, natural recharge, and the available waters, that is around 60%, and the evapotranspiration is around 1500 kilometer cube. But this is not the actual figure. There is a very catch in understanding this part of evapotranspiration. The available estimates are 69% and the 40%, as compared to the other countries here. Australia, the evaporative component is around 90%. So this part is very least understood in Indian hydrological cycle. So we need to address this issue: how much water is evaporating annually from this total available water from the Indian nation. So then in this condition, what we need to do? We need a fundamental research to increase the water availability for user, that is usable water, not the available water. We need to increase the utilizable water for the users. Then we need a fundamental research. Where is the water resource, how to exploit in a scientific way. Then applied research, that is water quality, how to clean and process the water for the users for different sector, what are the quality for drinking water, domestic uses, agriculture, and the industrial uses. Then we need to develop engineering developments or the engineering structures to store and make it cost-effective portability of the water, to make it very convenient for the users. So presently, the ongoing research in Department of Earth Sciences are glacial lake outburst flood related issues, river dynamics, surface water groundwater interactions, saline water intrusion, particularly in the coastal regions, riverine sediment load and erosive actions of particularly the Himalayan rivers, and the rejuvenation of drying springs in Himalaya, as Professor Pandey discussed. Almost the 50 to 60% springs of the Himalayas are drying. So we are working on this aspect, what we can do and what are the main reasons of this drying of springs, and the estimation of actual evaporation from running water. This is very important parameter to address the actual Indian hydrological cycle, how much we are getting, how much we are storing, and how much going back to the atmosphere. So for this, we are using various techniques, tools and techniques of remote sensing and GIS, and we have some equipments like ionochromatograph, IRMS, and this IRMS isotope ratio mass spectrometer. This is one of the most high-end machine. In this machine, we can measure not only the conventional isotope, something like delta OH and delta D, we can able to measure the dissolved nitrate content in a water, and we all know the nitrate is one of the important parameter to understand the point source of pollution. Apart from this, we are also developing teams. That teams equipment can measure the unstable isotope, particularly the strontium and niobium. As the Professor Ahmed discussed, the sediment load. That sediment load parameter can be understood by just taking a 1 liter of the sample from different part of the Ganga and measuring that strontium content as well as their isotopic ratio. We can estimate the seasonal, monthly, bi-monthly, the different sediment coming from the Himalaya. Basically, the Himalayan rocks, except Shivalik, most of the Himalayan rocks are marine origin, and the marine rocks having typical strontium content. Using that strontium content, we can easily estimate what is the sediment load of river Ganga at different location and different season or different months. Then we have some geophysical equipment like electrical resistivity tomography and magnetotelluric gravimetry and other geophysical technique to understand and monitor the hydrological aspect of our nation. And with this, thank you very much.
Friends, as we have seen, water is a vast subject, and various departments are working in different aspects of water. HID is putting a little effort, apart from the formal education in the form of 2 master programs, water-related area of power and environmental management of water bodies. Our research areas are mostly on the hydropower and environmental management of water bodies. In addition to that, we are also working for the research work in the greenhouse gas emissions and mitigation in the reservoirs, ponds, and rivers. Also, for the review work on the sewage treatment plants. And wastewater treatment and recycling, resource recovery and circular economy is a vast area where we are working, and presently we have around 50 research scholars which are working in different aspects. Now, HRED, since its inception in 1982, is working as a one-stop organization for all the aspects of hydropower development, right from concept to commissioning. All kind of troubleshooting problems during execution, but also tackled by the department. And we have developed a real-time digital hydropower simulator for the human social development in the field of operation and maintenance. Livelihood activities through micro-hydro in the remote hilly areas. Development of water mills, where 2 patents have already been awarded. We have set up world-class turbine testing laboratory. And sediment is very important because most of the hydropower they are in Himalayan regions and sediment is a major problem. So we also set up online sediment monitoring system and everything testing laboratory. There is a tedious task of field performance evaluation of hydropower stations, where we have tested more than 300 power stations. And recently we are working on the development of hydrokinetic prediction. And we have prepared 27 manual standards for different aspects of the small hydropower. This is the Rnd Hydrocarbon Laboratory. This is a world-class facility developed in HRED. And the real-time data center where the training is imparted to the operation and maintenance persons of the power stations. Then sediment monitoring and impact analysis laboratory. Here, this is a power plant at a village Kakroi near Haryana, near Sonipat in Haryana district, which is about 50 kilometers from Delhi. And here we worked during the period 84 to 88. And concept to commissioning, it was done. And here the 4 turbines were installed of 100 kilowatt capacity. In fact, it was a field laboratory where the performance of 4 different types of turbines were tested at one place, which were manufactured by different manufacturers from different countries. Then another project which was we worked for almost 16, 17 years on a Mukerian in Punjab, near Pathankot. And we prepared DPRs and detailed engineering designs, specifications, design, and we were involved during all phases of the construction. As far as the environmental management of water bodies is concerned, it was started in 1999 with the procedure project of conservation and management plan for Dal and Nagin Lake in GNT. We worked on various lakes and we also prepared techno-economic appraisal reports of various lake projects, STPs, and also prepared guidelines for National Plan for Conservation of Aquatic Ecosystems. Now, we are also working on the treatment of wastewater, which comes as the municipal wastewater or from the reject water from RO systems and hydroponics wastewater, and to get the energy recovery in the form of bio-oil, biochar, and biogas. Then in the water quality, we are also working for GHG emission assessment, water quality mapping, water reclamation, Ganga river rejuvenation, environmental impact assessment, river monitoring using microinvertebrates, where we carried out one project with the help of European Union. We have 7-8 countries were involved. So that way we are working in all aspects of the water, right from the energy generation and the wastewater treatment. Thank you very much. Now I request Professor Arun Kumar and Ms. Kirti Goyal to come forward. We have prepared a publication which was mainly prepared by Kirti Goyal and Mr. Professor Arun Kumar. Shali and Kirti, they can come forward and put this publication for release to Director IT and Director NIH. And we acknowledge the contribution here, the text review by Professor Piyush Chetna and Professor M.L. Kansal from WRDU. Photographs of the case studies by Professor A. Kazmi and Namit Saini, and graphics and sketches by Ms. Shali Bhavle from Greenhouse Green Committee Office.
Say something.
And a copy of this publication is available here. After the meeting, those who are interested, they can have a copy.
Basically, this publication on the water reuse, because we had to give the value of the water, and reusing of the water is one of the easiest, or is one of the things which we can see easily. And you'll be very happy that Hydrology has started reusing its water, which we generate through the sewage. Out of 3 MLD, 1 MLD is right now under, some of them is already working. In the sense, some of the water is already used in our campus, and some of the photographs have been given at the end of some of the good examples in the country. So it has got what kind of awareness, policies, what are the difficulties, challenges this particular sector is facing. Because water is valued only where there is a scarcity. Rag do piche, bhai. Piche rag do. So water is scarcity is felt only where, the value becomes very important where there is scarcity. If there is no scarcity, like in Ganga plain here, people don't feel the, importance. But those areas like Gurgaon, for example, Chennai, Pune, Nagpur, one of the things, and there are some excellent examples where economic viability is set up over there. So those examples are quoted here. This is also on the website of the department. We have placed the development, and this is a special publication on the water day. So, you find many texts here and there, but a special publication on the water day, and I think that is which at the beginning, which, is, and this will be for interest for common public also. The illustration, and I would like to say we have a Saili Bogle. She has joined Green Office of the Institute. She has an excellent work in creating the sketches and the graphs, which sketches especially for common public to understand. And then, of course, Kirti as a research scholar, she is on her final stage of completing on the work on the water use. So they are the one who have contributed a lot. And Bihu from the City Department, she has been very kind to review the text. And of course, other colleagues also contributed one way or other. And that's all from my side. Thank you.
Now I request Professor Rnd that I will enlighten us.
My dear friends from NIH, Dr. Kyabi, all scientists from NIH, my colleagues from IIT Roorkee, from all departments who work in the area of water. This program has been done very efficiently. So just 1 hour exactly, and sticking to the time and coming to the point exactly, and everybody's presentation was very focused. I think all the presenters need a round of applause. We should have been celebrating World Water Day for, I don't know since when, but at least 2021 we have started, and I hope NIH and IIT Roorkee will continue this forever. This can be one day when we can truly come together without any external involvement. RWC is our event which is open to the external world. But this event is primarily focused on our presentations, on our knowledge, on our facilities, on our skills, on our strengths. So let this today's function become a model for subsequent years. And even sitting here for 45 minutes, you can clearly see that everybody brings something unique on the table. This is what is important. All human problems of mankind, they don't come in silos, or they don't come in baskets that this is a civil engineering problem, this is an electrical engineering problem, this is a water management problem. No. You need a team. You need a multifaceted approach. You need a multi-pronged strategy if you want to make a difference on the ground. If we have to publish a paper, we may not need it. And of course, we all want to publish papers, but we want to go beyond publishing papers. And that can happen only when we come together, only when we join hands, only when we take back today, okay, let me talk to this person, let me create a collaboration with this aspect, whether it is from civil engineering, whether it is from WRDM, whether it's an agriculture aspect. I'm sure our scientists from NIH will also find some value in creating these partnerships. And yes, there will be occasional hiccups, there will be occasional problems, which are very natural because whenever two different entities come together, there can be teething problems, there can be settling down problems, or there can be problems because of some past happenings. So let's keep them behind. Let us find out areas where we can collaborate, where we can work together. If there is a difficulty in some area, that should not prevent us from moving ahead. If we focus on our areas where we can bring value to each other, that will add value to everybody. And I tell you something interesting. Just yesterday at 8:30 p.m., I was having a meeting with our alumni batch who was having a Silver Jubilee reunion. And they came up with a very wonderful idea that how they want to give back. And on their own, in the presentation, they mentioned NIH. So these are students who have graduated 25 years back, and they are thinking what we can do for the alma mater. And they are saying that, okay, they also mentioned several other things. So even people from outside, when I say outside, I mean people who have left the campus, they also feel that, yes, there is a potential for something unique coming out of this. On the other hand, I tell you one more story that I told just today morning, and it's important for us to hear that story also. That one of our alumnus, 1948, when I say our alumnus, I mean the University of Roorkee, IIT Roorkee. So 1948 alumnus, who passed away a couple of years back. His daughter, she retired as a IS officer, and I think Gujarat cadre. She worked in the state and the center, and she held several responsibilities related to water sector. And I was talking to her, in my capacity as director IIT Mandi, because I'm holding additional charge of that. She wants some collaboration with Mandi, and she mentioned that my father is from IIT Roorkee, and I have very deep emotional connect and all that. And when she mentioned about water, I said, do you know what is the water capital of the country? He said, what do you mean? She could not understand the question. I said, it is the name that you are taking repeatedly. She did not know that NIH is here. She did not know that we have Department of Hydrology. She did not know that we have Department of HRE. And the mistake is not of her, mistake is ours. ये हमारी गलती है कि कोई वाटर सेक्टर में काम करने वाला ब्यूरोक्रेट जिसका इमोशनल कनेक्ट है रुड़की के साथ, उसको नहीं पता है हमारे बारे में. So it is very important to today's world that we reach out. And I felt it was an eye-opener, and I invited her, and she will be coming with her team, and I will ask all of us to give time to her and showcase. She did not know that we have multiple departments. She did not know that we have NIH. She did not know that we have Irrigation Research Institute. She was not aware of the canal and the history and all that thing. So I told her in detail. And then I reflected, yes, it is my mistake. It is our mistake. It is not her perception gap, but we have not done enough to reach out to the world. And this partnership is meant to reach out to the world. Both the organizations will gain from each other. More importantly, the country will gain. I think we may lose or gain once in a while, but if the country gains, I'm sure all of us will be happy. So well begin, wonderful beginning, wonderful inauguration. Next year, I think the coordination committee should decide who will host this function next year, who will come out with the publication. This publication should also become an annual event. Whichever department or organization, NIH or whatever, hosts the event, that should bring out the publication, and it should become maybe even a 2-hour event. We can make a 2-hour event, have slightly longer presentations. And the presentations from next year onwards can probably focus on the recent work done. Today also some presentations were on recent work, but some presentations are talking about their core strengths and facilities. But next year onwards, I think we can skip, I mean, de-emphasize that part, emphasize more on what we have been doing in recent times, so that we can be more current of each other's strengths. So I think I would like to compliment HRED, Professor Singhal and Professor Arun Kumar for their commitment and leadership. And I think coordination committee should meet so that we can decide the next year.
So there has been offered target WRT of the groundwater, because the next year you went talking to the groundwater.
Okay.
That has been already offered.
Okay.
But sir, not only one publication. If there are more volunteers to make the publication, you have more than one answer.
So at least one.
Yes.
At least one. Right? So one should definitely come. So Sitagi, can we say WRDM next year? Okay, so WRDM will take the responsibility of holding the World Water Day event next year on 22nd March 2022, right? And of course, everybody will be invited. It will be again an event of NIH and IIT Roorkee, and this is how we do it. So thank you all for coming and joining this conference.
Thank you, sir. So here's the time for vote of thanks. Thank you everyone for joining, making this event a grand success. First of all, I'm thankful to our invited speaker, Dr. Gwyn Rees, Head Water Resources, UK Center for Ecology and Hydrology, for accepting our request to deliver a talk on the theme of valuing water. I'm thankful to Professor A.K. Chaturvedi, Director IIT Roorkee, and Dr. J. Vitagi, Director NIH, for expressing their views on water and motivating us to conduct such events in subsequent years. Special thanks and hats off to the heads of different departments of IIT Roorkee for briefing about the R&D activities and initiatives undertaken by each of their departments in the field of water. Finally, I am thankful to all the faculty colleagues, scientists, staff, and students who have graced this celebration of World Water Day 2021 online and offline. Need of the hour is to safeguard this critical resource of water for the benefit of everyone. And I am confident that different departments of IIT Roorkee and NIH will work hard together in this direction. Thank you and have a wonderful evening.